Today I'm going to talk more about OWL, and this will hopefully help you now as you're thinking about reviewing. But also I'm going to give you some more like background on OWL and what's going on and say the reasoners. But before then, before we even jump in, I don't know if I've told you, but I will tell you now. And if I have, I'll remind you. I sometimes have you do things we've already done in different ways because I would like to massage the information into your brain. And what I'm doing is I'm having you pull from long-term memory of what we've already done. And the more I get you in any given moment to pull from your long-term memory, the better those connections are, the more musculature you get in your brain juices. And so I am trying to build those long-term connections so that by the time that course is over, you don't have to, I don't know, find yourself in a situation where you have to think really hard about what was an interpretation. It will just come to you. That is how my brain works. And it's because I did stuff like what I'm going to walk you through now. With that said, DL interpretations, recall description logics. We got names, classes, and role names. That's the vocabulary. They're pointing to through this little .I interpretation, which is just a function that maps the names to things in a domain. They're pointing to things in a domain. A, under the interpretation I, points to that thing A with a superscript I. And you can just think of A as like an instance in the world, like Alex. It's the thing you're looking at from the perspective through the lens of the interpretation I. Same for C, that's the classes, and then roles are just, you're not looking at roles themselves as first-class entities, you're looking at pairs of things. And then that little delta symbol in I is just the domain. Yes.
Is role synonymous with object property?
Yes. In DL, recall.
Relation,
Yeah.
logic.
Yeah. So role, they're called roles in description logic, object properties in OWL, and relations to sane people like us. Example. So check this out. You have a list of names, a set of names like sun, the morning star. You have a set of class names like planet in star. You have a set of role names like orbits around and shines on. Make sense? That's your vocabulary. An interpretation, which is just that I equaling the domain plus plus the function that goes from the vocabulary to the world. That's what that .I means. Just that's the function. Define it as follows. There's a domain that contains these elements. Those little characters right there are supposed to be things in the world. You know, it's kind of tricky though, because we're writing a script, right? So like you can think of that circle with the dot in it as the sun, right? That is the domain. That's all that's in the domain. And you can define based on this an interpretation function, that .I is going from the vocabulary into the world, the domain, just like this. If you see the name sun, superscript I, that is equal to, the function is mapping to the sun. That's how you go from the vocab to the world. And then you have all these names listed out that are focused on these, they're pointing to these things in the world. And you also have the set of planets, the set of stars, the set of pairs of things that orbit around other things, and the set of things that shine on other things under this function. Draw it. Draw me a picture.
What are we supposed to be drawing? It's not clear to me.
All right. Great question. You should have a picture that represents the named entities in the domain and their relationship to one another. And you could characterize this as a picture of the sun and it bearing an orbits around relation to, say, what is it? Mercury, right? Or the moon or something like that. So putting this a little more abstractly, you should have something like edges and nodes, or nodes and arrows, and then labeling, you'd be labeling the nodes and edges, right? Like the sun would be a node. Orbits around would be an arrow or an edge. Does that make sense? Do you have all the instances in your picture? Are they all linked to something? If they are linked to anything at all?
I don't know.
Ha!
Getting there. Kind of.
Here you go. A little.
Wow, that is not how I drew it.
Ah. Orbits around, shines on. You have the star, a star class in the center, right? It's the sun. You have planets all around it, Mercury, Venus, Earth, Mars, etc. You have as well these relationships between the sun and various things. You see over here on the left, you have the sun shining on Pluto, which is not listed as a planet, and Pluto orbits around the sun. You also have the sun shining on the moon, as you can see in the upper right-hand quadrant, which itself orbits around a planet that is Earth, which orbits around and has the sun shining on it. But, you know, there's no orbiting relationship between the moon and the sun.
Oh, mine looks totally different, but I didn't use those pictures.
Yeah.
I use,
But you got it, right? Like the point here is reminding you of the focus of interpretations, how we go from a vocabulary down into the stuff that we want to talk about. There's like a mapping function that goes from the vocabulary to things in the world. And then the things in the world are often related as edges and nodes of this sort, right? And like fundamentally, when we're thinking about graphs, fundamentally, when you're thinking about object properties, right? You should be thinking in terms of the edges and nodes. Object properties are edges, and they hold between nodes.
but the edges and nodes are going to be between classes. They're not going to be between
Oh.
instances, right?
Oh, no. No. Edges and nodes hold between, when I'm talking about object properties, in OWL, for instance,
Yeah.
they hold between instances. If you were to have them hold between classes, then you would be in OWL full, the undecidable version of OWL. If we're thinking about the direct semantics, the direct there, by the way, the direct means instances. And so even when you like apply subclass restrictions on classes in Protege or something like that, the interpretation of that is that anything of this class, any instance of this class is related to some instance of another. So it's always instance.
Yeah.
Okay.
But what I meant, John, was like, star, the planet has orbit around star. The sun is an instance of a star.
That's right.
And all of our planets are instances of a planet.
Right.
But the relationship of planet orbit star isn't a relationship that's at the instance level. It's a relationship inherited from the class level.
No, it's the other way around. The instance level is where the relation comes from. The class level inherits it from the instance level. So you
Wow.
can't, if you were to apply the class, like object properties to classes, you have outstripped the expressivity of OWL with the direct semantics. You are now in that OWL full where you can relate things directly to classes. But here, like with OWL 2 and the direct semantics, whenever you're saying something that looks like it's about a class or a role constraint on a class even, what you're talking about ultimately in the logic is just the instance level. Now, when we say, for example, like, what is it? All continuants have some part or some continuant part continuum, right? What that means is, and you apply it to the class, right? Like you put a subclass restriction on it. What that actually means is any instance that falls under the class continuant has continuant part, some instance continuum. And that's all instance.
But isn't, like, when we look at Pluto, like,
Mhm.
Pluto's a planet, Pluto's not a planet. And
Right.
then one of the things is like, oh, well, it can't be self-determined in its orbit, right? But the reason why we say that is because all right, isn't that what it is? It's like that it doesn't have self-determination with its own orbit or something
Right.
like that.
Yeah, it's not in control of its own orbit.
But that's a case, that's a universal
Mhm.
for planets, that planets have self-determination of their orbit, and
Mhm.
then doesn't Pluto or Venus or Jupiter or whatever inherit that from the class?
There are two ways to think about this. Like you could think of it, and if you're thinking outside the expressivity of a language, and just thinking about it like in terms of laws of nature.
Mhm.
Like you could think of things like there being laws of nature that connect types of things necessarily to other types of things. Like you could think of it in terms of universals in that way. Like it's necessarily the case that planets are the sorts of things that have this kind of bounding or control over their orbits. That is very much like within the realm of possible interpretation. But when I say interpretation, here, at least in this context, I mean interpretation in the formal sense that description logic means it, in the OWL sense, in which case, if you're just thinking of it that way, then you are actually stuck with the another interpretation of that claim about universals, which is just as plausible, I think, which is just that anytime you want to say that about planets, what you actually, like at a class level or a universal level, what you actually mean is, instead of holding between universals, you're saying any instance that falls in this thing universals, this relationship holds. So they're just two ways metaphysically speaking of talking about relationships in the world. And there's like a lot of literature talking about like types of things being necessarily connected to other types of things, specifically David Armstrong, I'm thinking of him. But then there are other alternative interpretations which track much closer to the expressivity of this language. We're just talking about instances of things or like tropes. All I'm saying here is, if you're stepping outside the language, there are different ways to interpret the relationships. But if we're thinking of it specifically in terms of the expressivity of the language, our limitation, only one of those interpretations works.
But
Does
this
that-
language has a different expressivity
That's-
and limitations than say owl or owl full. Okay.
So definitely this has less expressivity than OWL full. It's certainly a lot less expressivity than like natural language, where we often are doing like metaphysics or these kind of like broader, more general interpretations, or even just science, right? We're talking about interpretations of the world, and we're talking about looking at it through a specifically inexpressive language that many of us use, but like it is a specific lens. And once you're looking at it through the specific lens, you starting to see the limitations of it. Then you have these other interpretations of the world that kind of outstrip that. And so it's very natural to be thinking of these like, well, how come I can't say that? Or how would I say this other thing in this language? And again, I want you to talk about this stuff here, even if it's a little philosophical, to get it out of your system. No,
John,
it will like work. It's good to work through it so you know, right? Like,
Yeah.
and John, isn't the expressivity of your type dependent upon the expressivity of your model? So like, for example, if we only went from material artifact to vehicle to car,
Mhm.
then we created types of cars or instances of cars, and we put every type of car we could think of in the
Mhm.
instance, that would be fine, but that's just not a very expressive model. But if we had a model that expressed that, hey, V8s
yeah,
are not the same as V6 engine cars, then you couldn't have a instance that had a V8 engine
Mhm.
with the same type as an instance that had a V6 engine,
That's
because
exactly
your
right.
model is more expressive.
That's exactly right. And when you're thinking of like being like adding more content or more specificity to your model in just the way that Jay's describing, you should think about this as ruling out alternative models. So if you don't say anything about like engines having parts, then as far as the language is concerned, you can allow for an engine that has a V6 and a V8 together somehow, magically. But if you want to exclude that, you have to say it. Remember, OWL is a language of the sort that's an open world assumption, right? Like just because you didn't say something doesn't mean it's false. So if you want it to be false, you have to say the opposite. This actually touches on another feature of OWL, which is OWL doesn't adopt the unique name assumption. So you can have one thing named or different things. That's fine, right? And reasoners will try to like figure out when those names link up and connect to the same thing. Just like in this sort of example here. Now, morning star and evening star, this is a famous example from Frege. Turns out the morning star and the evening star are both Venus. Like there was just different names for the same thing. It's for many years people didn't realize it was Venus. So they would call it a morning star when they saw it in the morning, call it an evening star when they saw it at night. And so like Frege was making a point, like you need something out in the world that is the referent of your cognition, where they thought it was a star.
Right.
Like they thought they were seeing Venus and they were like, look at that star. And everybody's like, yeah, what a cool star in the morning. All right, let me now move on to Tableau reasoning and more generally styles of reasoning. So your protege on your computer, like it runs reasoners. You've heard the word reasoners. Reasoning is just drawing out necessary consequences from sets of premises. At least in the way we're using it here. Strictly speaking, reasoning is what you do. You are reasoning. I will speak loosely in terms of that here. But so when I say reasoning, I'm going to be talking about drawing out consequences of that sort using often automated strategies. The sorts of reasoners that you see in Protege or in the DL community, they are a species of automated theorem provers or automated model checkers for like other languages. There are many other sorts of these things outside description logic. So here's an example, prover 9. It's a first order logic prover. So it draws out for much more expressive sets of axioms than DL allows, like inferences. And here's an example of a proof for like, I forget what it is, modus tollens or something, I forget. They often run by using resolution algorithms or unification or Tableau algorithms, basically proof by contradiction. And I'm going to show you more detail the Tableau stuff because the Tableau algorithms are the ones that reasoners in DL use. And here's a paper from Ian Horrocks, who was the inventor of Hermit. Again, one of the early pioneers of the description logic field. Like here, he's discussing transitivity or transitive closures and how they might lead to undecidability. So why we should have a more restricted language. Again, if you work through all of these papers, you'd know a lot of stuff about the logic, but they're very technical. I'm going to try to give you the tidbits where they're relevant. Just keep two things in mind. We're going to focus on the second one, but just so for your own knowledge, Davis-Putnam algorithms. These are algorithms that are used in broader, more powerful, algorithms for more expressive languages, like in first order logic. So prover 9, or at least its model checker Mace 4 works like this, where you basically they take an expression, a formula in first order language, and the algorithm will assign truth values, true or false, to predicates and parts of the sentences, as complicated as they are. And if it, at any point it reaches a contradiction, it starts over because it's binary, like true, false, start with all falses. And then if it hits a contradiction, it'll go back to the beginning and say true, false, 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 false. And it'll just kind of iterate through that recursively. And if it can get to a place where there is it can terminate when assignment is found for all variables and all possibilities are exhausted, then you've learned some information. If you get to a point where all of them lead to a contradiction, then your proposition is unsatisfiable. No, bad. You did something wrong. You said something like P and not P, right? Now, these are in contrast to analytic Tableau reasoning algorithms, which are the ones that we'll focus on because those are, again, how like the DL reasoning systems work, where you construct a tree where each branch represents some interpretation of a proposition. Then you decompose that proposition into its smallest parts. And then you do that so that in the interest of trying to either find a contradiction along the tree or in exhausting all the rules that you've used or you have at your disposal to decompose the tree, so you have an open branch. If you have an open branch, then there's a way to interpret that formula or that proposition so that it's true. And so it's not a contradiction. If you close all the branches, you said something wrong, like P or not P. And I'll show you more detail. I'm just giving a high level picture, but I'm going to show you an example of the analytic Tableau, because again, that's the kind of important algorithm for us. Before doing that though, I want to just highlight some reasoners that you've seen, likely if you're poking around in Protege. So you see Hermit, I was just mentioning that. It's probably the most efficient on balance in terms of like power and what it covers and speed. It uses not just the analytic Tableau method, but what they call hyper Tableau, which I'm not going to go into in depth here. It supports complicated description logic reasoning. It can handle just about anything that you're representing in Protege. It does take a lot of memory and it is slow on large ontologies. It is highly expressive though. You can represent just about everything you'd need to and run a reasoner on it to check it. Pellet, one of the earlier reasoners, it just uses the standard Tableau. It can support things like conditional reasoning with swirl. Incidentally, Hermit can as well. And it can also handle data type reasoning, so can Hermit. It is slow on large ontologies and its performance can degrade over time. In fact, very similar. It has some other optimization features. Mostly though, it's very fast for moderately complex ontologies. It's terrible with large ones. You might not even stop. uh, yeah, it's a kind of a moderately sized complexity. Elk, fastest of the crew, but it's because it ignores just about everything of interest. It is used for like very large ontologies that has no inverse roles. It doesn't really deal with object properties and role constraints at all. It kind of ignores half of everything you're going to use or anything you might find interesting. It's essentially focused on class structures and like some minimal connections between instances. Okay, that's a very high level overview of the reasoners, just to give you a taste. There's much more to say about each of them, and some of the things I said about one actually apply to the others, as you probably picked up. Okay, so the tableau, base tableaus work like this. They have these four rules. You have what you can think of as a conjunction rule. And I'm gonna let you stare at this for 2 seconds more than you have already. But instead of making you like work through this, I'm just gonna do this instead and tell you what it said in natural language. So you have a conjunction rule, just so it's clear. If you're given two classes on a branch, like remember the tableaus work by creating branches like that decompose like some complex expression like C1 and C2. Like that's a complex expression. You want to decompose that into parts. Like here's a rule to do it. If you have this on a branch, like it's a head of a branch, you can add C1 to the branch and you can add C2 to the branch. That's basically, this is just conjunction elimination, right? And the branch is helping you track where it's relevant. And again, don't worry, you're going to see an actual example of this in a second. I just want to talk through the rules. There's also disjunction rule. If you're giving C1 or C2, like class 1 or class 2 on some branch, then add C1 to a new branch and C2 to a new branch. And you can think of this intuitively as, cake or ice cream. How's the world going to unravel? Well, if I go with cake, blah, blah, blah. If I go with ice cream, blah, blah, blah. Think of the different branches as like different ways the world could be, depending on your choice. That's disjunction. This or that. Well, assume it's this and see what happens. Assume it's that and see what happens. That's how this rule works too. The branch is like separating the paths. For existential rules, and I made sure to put in the implicit universals out in front so you could see exactly what's going on. If for all x there's some y such that x is related to y and c and y is a c on some branch, then add that rxa and ca to a new branch, as long as a has not appeared in a previous line of the tree. If you're getting rid of, and this is kind of a general rule for whenever you're talking about something like backwards E, you can get rid of the sum symbol that, something's going on, something's creative. If I'm using creativity for Y, something's creative. If you want to get rid of the sum, you can do that if you pick an arbitrary thing that the creativity is about. And the way you capture the arbitrariness is that it has not appeared in a previous line or previous part of the branch or previous line up and leading up to it. And you'll know if it hasn't appeared in a previous part of the branch, it's arbitrary because you could have picked anything else of that type. You could have picked a B. You could have picked an E. As long as it didn't appear, you know nothing about it. It could have been any of the other instances. And that's how we go from talking about something to a specific thing and reasoning around what it could be. Does that make sense? Kind of a subtle logical point. I just want to make it clear. And then for the universal, again, you got the two universal x, universal y, rx, y. And this is the if then. If x is related to y, then c y, that is to say y is a c, and r x y on, and if that's all on a single branch, then you can add cy to that branch. That is to say, you can just break out cy from that conditional statement because you have both the rxy on that branch and this universal claim saying, if anything's RXY, then I get CY. Again, just to say, this is essentially modus ponens. If you've got this, you can get the thing that the arrow is pointing to and you can break it down. Observe, I'm
how would I
breaking
write that on
down complex expressions into their simpler parts. Yeah, Jay?
How would I write that on my computer? Like, is
Just like
there
that, I would hope, do you mean like in like natural language or just,
well, I mean, I don't know how I would do I don't know how I would do some of these characters.
so if you, that arrow, if you just do hyphen, uh, close bracket, then if you're using Word, it should convert to that arrow immediately. And then
Okay.
if you are, for that universal and the existential, I just copy the ASCII off Wikipedia because otherwise you can go into Cambria math and like do all that stuff, but it's a pain to work with. And so I just have it on my clipboard.
Okay, okay.
All right, let me show you an example. So is the following set of propositions consistent? That is to say, can you like expand them without a contradiction? And in the analytics Tableau sense, what this means is, can you expand them all into their constituent parts without closing all of the branches? The branches closing indicates that there's a contradiction on the branch, which you'll see in a second. So if I were to follow the Davis-Putnam algorithm, just for contrast, I would just go through and assign true, false until I, either got a contradiction or I found an assignment that was fine. For following the Tableau sense, I decompose all of this in a tree. I decompose it all together and I try to like find out contradictions and see if I can go on and on and on without running into something contradictory. And if I can, it's consistent because there's one interpretation, namely that branch on which I've assigned the variables, or I've basically assigned truth values, as you can think of it as, where these things are not in conflict with each other. So looking at the first, and at the top, you're seeing this is just that set of propositions. You'll see that the first one has an existential in front of it, that backwards E. And so I have to use this rule to break it down. So that's the rule I use to break things down. I only have those 4 rules. So when you're thinking of breaking this stuff down, you can only have 4 things you could possibly do. So the E is we say it has the widest scope. It's the thing on the farthest outside of the parentheses. So I know that's what we call the main connective. So I use the rule here. And what I do in that rule is I assign to some specific constant, some specific individual that has not appeared anywhere else. I assign it to the X in there. So EX is related to AX through A and F of X, right? Well, what do? Well, D. D has not appeared in any part of the other, like that. You see A over there, you see B over there, you see some X's and Y's, you don't see any D's. So it's fair game. So I've assigned D. That's how, and I've dropped the existential. Now I also break down the conjunction using the conjunction rule. So there was an and right there. I said, what can you do when you see an and? Well, one of the options is you can take it apart, all in the same branch, right? You'll see what I mean when I look over here a little further, because I'm going to break these down a little more. But here I can take off the universal as well. And how do I do that? I can instantiate, we call it, the y's to anything I want in the whole line. Like it doesn't matter if the y's have, or the b's in this case have appeared on a previous line. Why is that? Well, because I said every y. So it doesn't have to be arbitrary. There's a logical difference between some y and all y's. If I say some y and I want to get rid of the sum, I have to pick an arbitrary thing and talk around it. If I say all y's, I can pick anything, who cares, arbitrary or not, because I said everything in the domain is in scope. So when I strip off the universal like that, I can pick whatever I want, any of the constants, any of the A's or the B's or the C's, right? Or the D's. And in this case, I picked B first and I picked D second for a reason. I did it twice. And that was because I have SAD there. And remember what I said, if you have the first part of the line, if you have this SAB, which I have up here, as the consequent of the thing before this arrow, then I can infer the thing that follows the arrow. And that's like, I've done application of this universal rule in 2 steps, but hopefully you're seeing that like now I can get the thing the arrow is pointing to because I have the thing that preceded the arrow. And I did that by picking a specific instance that I knew was already there. Now we get to and I did it again because I have SAD there, right? So that's why I did it twice.
Wait, where did we have SAB?
SAB, right there.
Oh.
And then SAB
Yeah,
is
yeah.
from the conjunction. Okay, so now I've got these disjunctions, so I get to work with the disjunction rule. And this is where the branches become more obvious. Disjunction, incidentally, when you're creating branches, that raises the computational complexity significantly. Branching is a problem. Hermit, as I was saying a minute ago, has this hyper tableau that collapses branches. It's because collapsing branches is how you make efficient reasoners. The more branches you have, the more likely problems you have with the computation, because it has to run through multiple cases. Hypotheticals are problems for algorithms. In this case, I've got two of these disjuncts. I use the disjunction rule. What I do is I pick one side up and put it on a different branch. I pick the other side, put it on a different branch. There's already a contradiction, right? In my premises, I had BB. And now I've in one of my hypotheticals, I have, well, what about not BB? Well, what about it? Contradiction. So I close this branch and I'll put an X under that to indicate we don't have to do anything more with that. We're done. We found a contradiction. Don't go that way. Another disjunction. I have to apply that. I have to decompose as much as I can, right? So I have to apply the disjunction rule again, this time to D. Remember, because I have both I have 2 lines of disjunctions. So now I'm working with the second one. Again, found a contradiction, right? Not FD contradicts FD, which came about through that conjunction elimination rule up there. Hold on just a second. Okay, now I've closed 2 out of the 3 branches. And I don't really have much else to do. I don't have any rules that help me do anything with not BD. You saw I have 4 rules. That's it. There's nothing else to do. I got an open branch. This is consistent. Does that make sense? It's pretty interesting, huh? Maybe. It's mechanical. It's very mechanical and in some sense very boring. And it's so boring that computers can do it.
Why, can you explain why we have to branch to find or to conclude that not BP is a contradiction where it's in the every rule, like why couldn't we just look at the first line of the every rule and see not BP and just conclude that we didn't have to branch in the first place?
Yeah, there are different ways, like formally, that you can set up like this sort of similar reasoning. You could, in fact, introduce a rule, and in like Graham Priest's Introduction to Non-Classical Logics, where he uses tableaus at the heart, he has rules of the sort like modus or disjunction elimination, where if you have BB up there and you have not FD or not FB, you can just infer not FB without like having to close a branch or anything like that, because it just follows from the rule, right? It can't possibly be not BB or not BD, because that's a contradiction. So the rule disjunction elimination would help you just move through that. You're essentially, though, even there, you're like bundling up what I just did. And if you're thinking of it as an algorithm, like the step-by-step procedure, even calling a rule something like that, or like just moving, like what we would do normally as humans, just drawing the inference, you have to be very specific for the machine, right? Yeah, you have to like walk it through all the steps, and you have to feed a machine an algorithm that it can walk steps through just like this, or it's going to go crazy. It's going to be generative AI.
Yeah.
I'll to pause. Are there any questions? Because as maybe intellectually challenging as what you've just seen might feel, nothing in your life has prepared you for what we're about to do. So I'm going to pause. Jay, you were saying?
So when I was in the army, I didn't know calculus, but I had to learn like 25 different calculus formulas for how interpolation from satellites happens and how IO, RP, and all this stuff happens.
Yeah.
And then basically the day after we finished the test and did all this stuff by hand, they gave us a computer system that did all of this. So is a lot of the Tableau reasoning we were just doing there, because you said at the end, computers can do this. Is this almost like an appreciation for what automated processes can do for us? And we want to understand these things so that way
Oh,
we,
no, no, I wish. So the reason I am walking through this is because I'm preparing you for R&D downstream, because these algorithms, as good as they are not that good.
okay,
The Tableau methods could be better. We are just stuck with OWL because there aren't a lot of people who understand how these things work. And I think if there were more people who understood, not just appreciate, I mean, I appreciate analytic Tableau methods, but I also recognize that there are different things we could be doing. And so I want you to understand enough so that later when we get into some other projects, potentially can make real progress on moving the field forward, maybe outside of OWL. In worst case scenario, even if we don't, by trying to break it, you're really gonna understand OWL.
yeah.
You're gonna have to, right?
I know Barry's talked about how he thinks we should be moving away from OWL in the
Yeah.
future.
I think a few people do. It's just, it's hard getting there, but I wanna, part of this class, not entirely this class, part of this class will be getting over that learning curve. I don't want you to have to go read Horrocks. I mean, you can. I don't want you to go read all that stuff. I'll do my best to distill the highlights and then, but in addition, teach you the sort of mental strategies that logicians use so that you don't need to read Horrocks. You can kind of like intuit like they do, like he did, what sort of options might be in the playing field that are better, or at least worth exploring.
Yeah.
But yeah, I'm not to back to your your education there. I am definitely not the sort of person who will teach you algebra just to give you a calculator. Like, that seems like a waste of time to me.
So are there currently other alternatives out there, and like the main barriers just kind of habits of using OWL and like the challenges of learning these alternatives?
Yeah, there are a couple of reasons. So a lot of it is what you just, the second part of what you said. There are some people who are like trying to do the sort of stuff I'm describing here. There is one group that is they're using first order logic axioms, which are more expressive than OWL, and they're using them as annotation properties on in OWL files. And then they have like scripts that will take the OWL in the OWL files and they'll translate it into first order logic, and then they'll combine that with the axioms and the annotations, and they'll run like first order reasoners on it as a way to try to, respect OWL, but also, be able to infer some more interesting things. That's a cool strategy. I think the hindrance though is that they cannot and haven't been able to infer anything interesting and then put it back in OWL. And so like they're almost there,
I
right?
see.
Like, yeah, so
Yeah.
what they end up doing is creating a model that if you were using a more expressive language, would be fine. But if you were using a more expressive language, why would you be using OWL at all? So
Mhm.
I saw what they were trying to do. There was a DARPA project funded recently, although I think the whole project was just killed also recently. But the project was on scaling automated reasoners of a first order sort. The way the quote unquote winning team had pulled it off was that they had combined automated theorem proving and model checking with machine learning strategies, because it turns out that they had this very good insight, which was if you're looking for a proof of something, you only have to find one and you're done.
Mm.
And so what
Mhm.
they did was they used some NLP and ML strategies to like basically do like distributed parallel searches for an oracle, i.e. a proof. And
Hmm.
and they were like, people didn't think of this because they were suggesting, I think you're probably right. They were like, people didn't think about making this connection because when you're using machine learning algorithms, you never get an oracle. Like you never get a proof.
Mhm.
That's not what they're
Yeah.
going to do. They're statistical. And so, but if you connect these two, then like all you need is one, and then you can feed that proof back and like prove other things using it. And so that to me is the way to go.
Mhm.
So connect, like I like to think of this in terms of like bigger architectures that we could be employing. So automated theorem proving's out there, there's a lot of research on it, but it's always isolated and focused on specific toolkits. Same with OWL, same with machine learning, folks. But if we bring all of the artificial intelligence tech together, I think we might be able to have a bigger boat, if that makes sense.
Yeah, that's interesting.
Yeah.
Thanks.
Here we go. Welcome back. For those of you unfamiliar with the zebra puzzle, you may know it under different names, like the Einstein puzzle, the puzzle that nobody could solve but Einstein, blah, 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 not true. The puzzle is 15 claims and a question about them. Actually, 2 questions, but we'll get by with just one. The puzzle itself, I think, is straightforward enough. You do some logical inferencing. If you were to write this out on paper, things about 5 houses, an Englishman living in a red house, blah, 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 the greenhouse being immediately to the right of the ivory house, etc. If you were to write this out, think about the logical consequences, what you could infer immediately, what you could infer conditionally, what you can infer indirectly. You'll solve the puzzle, which is just this. You answering this question: who owns the zebra? Note, zebras aren't mentioned. One of the inferences that there's a zebra. And then you got to figure out who owns it. Everybody owns something. Zebras among the animals that could be owned, stuff like that. So again, if you wrote this out, thought about it, I don't know how long it'd take you, but it'd probably take you a minute, but you figure it out. You'll figure out who owns the zebra. You'll also figure out who drinks the water, which is the second question. It's just as easy to solve. I mean, it's on par in terms of difficulty. I'm not interested in you solving this on paper. I'm interested in you solving this in Protégé. This puzzle is straightforward enough on paper. I want you to represent these 15 statements in Protégé using OWL. And then I want you to run a reasoner that tells you who owns the zebra. Now you may be thinking to yourself, John, this is impossible. You're a madman. Not both of those things are true. One of those things may be true. Now, I only know one person who's done this, and it's me. Everybody else who said they did, when I looked at their proof, they were wrong. It is the hardest puzzle I've given to class. And I want you to solve it. So open up Protégé, work together, start representing the stuff. Again, with the goal being that I would like for you to push a button, permit, or some one other reason, be able to push a button and infer what person, what are these instances of Englishman, Spaniard, etc., who owns the zebra?
How much time do we
The rest of your lives.
have?
Ali is still working on it.
Want us to do this using BFO and CCO, or do you just want us?
Either way, like whatever's easiest, I don't think it'll help. BFO might make it more complicated because you'd have all these inferences, all these like subclasses you have to work through. Just get through it without it if you can.
You just want us to build just a very siloed kind of ontology to.
That's fine. Yeah, because this is mostly about getting you really familiar with OWL and what it can do and what it can. I mean, I've presented this to experienced ontologists before, and they were like, you can't solve that in OWL. Well, yeah, you can. You absolutely can. I'm gonna make a breakout group so that you guys, if you want, because I think it'd be good if you could talk to one another. So I'll make a breakout room and you guys feel free to discuss. It may be helpful. Do it on paper, but
Drunk in the greenhouse. Coffee is drunk in green.
Cool.
And then next we got Ukrainian drinks tea. Ukrainian drinks tea. 6, greenhouse is immediately to the right of the ivory house.
So John, what we did is we created classes and then we just created a groups of instances under all the classes, and then we're just asserting
Yeah, so
all
we
the
have-
relationships inside of the instances.
That's what these jokers did too.
Oh. You're making it sound like that's wrong. Okay, where are we? We're at the,
No, I just love that expression.
okay, so the greenhouse is immediately to the right of the ivory house. How did we want to do that, green? Where's green?
Just put the greenhouses to the right of the ivory house.
Well,
But I don't have a relationship for that.
Yeah, you do. You have, it's immediately, I think we wrote it. It's rather complex. You might want to go copy it.
Oh, to the left of, to the right of. Right. Okay, got it.
but how is
Green-
that gonna make clear that there's nothing in between the two houses?
Oh, so you should have the word immediately in there. You should go back and change it. Obviously, this is a terrible relationship. I've never built it this way, but for this, it works. Yeah.
Okay, I'm just gonna have to.
But
make
yeah, it
a
has
new
to
one,
be
I
a little
think.
bit more expressive.
Immediately to the right
Left
of,
up and to the right
to the
of.
left of. See, this is not how you spell immediately.
Nobody ever said you had to be a good speller.
Immediately. You know, it's just worse when people are watching me.
It is really bad. And Protege has zero spell check anywhere.
Okay. Delete that and then immediately.
We lost our connection with immediately to the left. Could have copied it.
The left to the right of.
Right, the connections.
Kelly. Yeah, I gotta re-add the inverse because it's not
Yeah.
letting me like change the name, and I'm not gonna worry about how to figure that out right now.
Fine.
That's okay. Inverse of to the left of.
Yep. There you go. Good.
Fantastic. Okay.
Now we can go and make
Individuals.
that.
So green is.
Greenhouse is immediately to the right of the ivory house.
The right of. See? This is why I need to be a good speller.
You do not
Where
need to be a
the-
good speller.
Just go copy and paste it, seriously. The easiest place to copy and paste it. Well, hold on. Go to the three little lines. Look above where it says
Oh
immediately
yeah.
right of, up in the blue. There's three little lines. No, over to your right. Over to
Of
your,
annotations.
up above. Up
up.
above annotations. There's three little lines. Three little lines. There you
Got
go.
it. Copy
Now,
IRI.
now go to copy IRI. Now go to your notepad. Go to your notepad. You don't want to put that in there. It's going to give
Like,
you all
open up a notepad. He's saying
open up your
separate,
notepad.
like a text file.
Oh.
There you go. Now
Got it.
copy it in there and then just take off the end after the slash.
Oh, I see. Funny. Okay. Green. Immediately to the right. Green
Ivory.
is immediately to the right of the ivory.
Yeah.
Ivory.
Okay.
Old gold smoker owns snails. So this is gonna sound like the old golds own the snails, though. This is where
Well,
I
we don't know. We don't know.
we don't know who smokes
Old
the old
Gold
golds.
Smoker is, right?
Yeah, so I can't assign that to a nationality and then say this
Well,
person
then just
owns.
do this. Just create a instance, call it person X.
Oh,
Because we don't know who person X is, right?
person old gold smoker.
No, because because person X is smoking old golds.
Okay,
So-
are we gonna remember that person X is the one that smokes old golds?
Yes,
Yeah,
because
why
we're
not
gonna-
just label it the
Oh,
old
add the
gold
create the
smoker?
relationship right now. So now, right after you create him,
Are we happy
you
with
don't
this?
need that. You don't need that because you're going to create a relationship with person X as who smokes old golds, and he's the only one in the whole problem.
Person
who
X.
smokes old gold.
Person X smokes
Yep, old golds.
old golds.
Smokes isn't right for some reason. I don't know.
Smoked. Oh, that's the issue that I had. I misspelled it.
All right, well,
They
just
smoke by
whatever-
smokes.
however you
Smoked.
said it, just put it that way. It's still wrong. I don't know.
But so Old Golds looks like an instance right now, no longer a class,
Old Golds was never a class.
but it
Old
would be a
Gold.
kind of,
It's
I guess I,
the
yeah, I
type
could
of
think of two.
six. It's a type of six.
Yeah, exactly.
I'm just gonna fix this because I'm gonna screw this up again.
Like it doesn't, like the smoker doesn't just smoke like this particular cigarette, like he smokes like Old Golds in general, it seems like,
Yes.
Smokes is smoked by.
which implies the instance, I guess.
Okay, person X. Oh, it's probably because I capitalized it, guys.
It doesn't matter.
Person X.
What-
Is that why it was?
No, that's
No,
not.
okay.
It's because you. It's
Um,
because you haven't inserted to a type. So here, go
right.
make the
Okay,
person.
person.
Yeah, you can do it in the other one too, but you can do it there. Yeah, okay.
Okay,
That's why it's bold.
Right.
Protege is really weird. So if you make an annotation or you make a relationship in a class, it turns bold, and then it only turns bold if you make it a type within your class structure.
Okay, smokes
I don't-
Old Gold. Person X owns snails. Wait, no. What is it? Person X, the Old Gold smoker owns snails. So person X
Owns-
owns snails. Okay, owns snails. Cools are smoked in the yellow house. So person Y. Person Y lives in.
Yellow
Oh, I
house.
haven't added the thing. Person Y.
We're gonna have a lot of person X, Y, Z, A, B, C.
Yeah. Person Y lives. Oh, housed is housed. I don't know why I wrote it like that, but
We don't have a lives.
No, I had a major brain fart while you guys were all speaking, and I
Okay.
just called it. No, I didn't. Lives
I'm-
in.
Lives in.
I'm just worried, like with the person X and person Y, like right, like the person who smokes Old Golds might end up being like the Englishman or something
Yeah,
like
but
that.
then I feel like you could
That's our
say
goal. Our
that.
goal is to figure
like,
this out.
Then
Yeah.
you could say person X equals Englishman, can't you?
Like an equivalent.
Yeah, you can say their equivalencies. Yeah.
It's not like just because we're making multiple like people doesn't mean
Yeah.
that they're not the same people, that they're all individuals,
Yes.
even though it's called individuals.
Yeah. Okay.
Okay, person
Makes sense.
Y, where are we? Person Y smokes cools and lives in the yellow house.
Whoever was asking that question, see under types, you have same individual as. So if we found out that
Oh.
person Y was the Norwegian, we'll just say person Y is the same as Norwegian.
Yeah. Okay. Nice. Thanks for pointing that out.
From
Oh, wait. Okay, wait. Person Y smokes, cools, smokes in yellow house, lives in yellow. Right?
no, we
Okay.
don't know that. We don't know that.
Cools
Because
are smoked in the
Cools
yellow
are
house.
smoked in the yellow house. So person smokes them in the yellow house. So we don't know if that person lives in that house. We just know that he smokes cools in the yellow house.
But we don't have a smokes in like a smokes in. We just have a
Well, we can make a smokes in
okay.
another relationship. Yeah.
Lives in yellow.
We can still keep. Oh yeah.
Okay, so
Is this making
Smoke.
sense to everybody else?
in.
Yeah.
Okay, so
Okay. If we're saying something that somebody completely thinks is contradictory or disagrees, just.
I'm just on my own trying to think of a
yeah.
different way to possibly model like next to and immediately to the left of and like I'm just trying to think through that myself.
I think there is, right? And you would use, but the thing is, we're trying to do this quick right now. We're not
Yeah,
trying to
yeah,
use,
yeah.
as John said, well, don't use BFO because it's too complicated. But yeah, like, I think that
Okay.
you would bring in ontologies that are more expressive with cardinality. Yes, I agree
Yeah.
with you.
Okay, are smoked in. No, wait. I'll just leave it at that. I'm not going to make an opposite for that now.
So what I would do
Uh,
is I wouldn't apply that to person Y. I would apply it to the cools.
Is smoked in. Blank is smoked in. So smoked by is smoked in. Okay.
And what I would do is did you what was the other relationship with the cools? Because
I'll
I
be
think,
right. Yeah.
I think
So
we said a person.
person Y smokes cools.
We don't need a person Y because we don't know if there is a person Y or if it's transitive and there's like 5 people that smoke cools in the house. Maybe everybody in the other 5 houses goes to the yellow house and smokes cools. We don't know. All we know is what we should be representing, and we know that cools are smoked in the yellow house.
So no person Y. Cools are smoked in. Do I have that other copy? Is smoked in. Cools is smoked in.
Yeah, so go to
Cools.
cool.
Cools is smoked in. Yellow.
Yeah.
Milk is drunk in.
The middle
Middle.
house.
Is drunk in. So then, do we have positions then?
Well, we're
Do I
starting
need to add this relationship?
right? So we're gonna have to have, so now this is the question. We know we have 5 houses. Do we want to have house position as a class and then just have position 1, position 2, position 3, position 4, position 5? And then we could just say that
Position 3 is middle.
then we don't have to use the word middle. We could use milk is drunk in in house position 3.
Well, you're
But-
gonna have to, because cools are smoked in a house next to the house where the horse is kept. So you're gonna have some. I mean, 1, 2, 3. I mean, how are you gonna?
Differentiate the positions in terms
yeah,
of left, right?
linearity.
And
Well, I don't know. I mean, we have the word middle, right? We have the word first. So do we want to say the first, second, middle, fourth, and fifth house?
I was thinking like if we're using something like a next to relation, right? Like the first house could be represented as like the house that has, no house next to it on the right and all houses next to it on the left or something like that. And then the middle one could be like 2 houses next to it on the left, 2 houses next to it on the right.
But should we also use the language from the puzzle? And the language from the puzzle, like Tim said, we have the middle house, right? And so my whole like, hey, have it 1, 2, 3, 4, 5 ordinal positions, that doesn't really make sense. So I mean, we could do both because you could have equivalencies. here.
Yeah.
I think middle is an important word that we have to have here. So having maybe first, second, middle, third, fourth, and then if you want to then convey, what third or fourth is or second differently, you could then say that, it's an equivalency.
okay, I'm
Right
gonna
here.
come back to middle. I'm gonna move on to the next ones, and we're gonna
All right.
add the 9, like the middle part, in a sec, so that we can just keep adding the
Okay,
relationships
well,
that we have. Does that work? Oh, but then
Yeah.
right after that is
Yeah, but you
lives in the
need
first
that. So
house.
why don't we just put in middle first? Why don't we just put it in the ones we need?
Yeah, okay.
now, and then we'll come. We don't put in like second and third and fourth until we need something like that.
Position, house position.
Yeah, I would say house positions. I mean,
First,
very BFO, but that's okay.
middle.
This is weird for my brain, Tim.
Yeah.
I've been so programmed to be so CCO, BFO.
Okay, so all we have right now are middle and first for that.
Fine. That's fine.
Why
for me.
not? Why would we do like right of the Ivory House?
You don't, do we
Yeah,
have it?
That's not like a, we don't
No.
know how,
Next
I
to the
think that's
blue
the
house.
relationship though.
I thought it was the position.
Well, no, I mean, to the, no,
It's like a relative position.
it would be,
Yes,
we already
I-
have that, immediately to the right and immediately to the left. We have that relationship.
Okay. Fuck, where was I? Okay. Excuse my language. Sorry, guys. Milk is drunk in.
Where the hell's the horse kept?
Is drunk in. Okay. Milk is drunk in middle. Middle.
Yeah.
Did I do that for yellow? Why did I do that for yellow?
You would have middle is where milk is drunk.
Is drunk in milk. Middle. I had applied to yellow by accident instead of milk. That's what I was fixing. Okay.
We have an in
Norwegian.
or is drunk. I guess we don't need it. We don't need it. Never mind.
Norwegian lives in the first house. Norwegian
Now we need to have a position which is the first. That's fine.
lives in first.
By the way, you can just create that first here in individuals, and then you can just click on the type and then just associate it with.
Oh, okay. That
position.
works.
You don't have to go all the way out and do it. Yeah.
Man who smokes Chesterfields lives in the house next to the man with the fox. This
But have we
insinuates
done
that
the-
there's a
have we done the
singular
first one
man that smokes Chesterfields.
Hold on. Have we done the Norwegian lives in the first house yet?
Maybe we should be like person 1, person 2, person 3, person 4, and then person 1 is Norwegian. Person 2 is this.
Will we
Or like let it.
how would you determine what person 1 is? Because
Oh no, like the 1, 2, 3. I mean, you can call them A, B, C, D, and they can live in house 1, 2, 3, whatever.
well, we don't know if anybody lives in all the houses.
Yeah, but you don't have to. You don't have to say that. Like
Yeah.
when it says
I
the
think we know
man.
we have equivalency. We have the ability to have equivalencies. So if we do have person Y is the Norwegian, we just make that equivalency at that time once we find out it's true. I don't think we have to presuppose it. We should try to keep the model as simple as possible.
Okay, so do you want me to just add in another person, like person Y, person Z, smokes Chesterfields, lives next to person B that owns the fox?
Mhm.
Okay, now I don't have next to. Do I make next to? Do I
Yeah.
make immediately to the right of and immediately to the left of a sub property of next to?
You could, yeah.
Okay.
Yeah,
Next to.
because everything next to is going to, well, no, you would have to have next to would be different than you. So you could have next to, and then you could have to the right of and to the left of, and then you could have immediately to the right, immediately to the left.
Does
know-
next to not insinuate that it's like immediately to the left or right? I
No.
wouldn't say something like 2 houses over is next to me.
No, because if you're looking from a geospatial perspective, it could be behind you or in front of you is still next to you.
Yeah, but then couldn't I just say like immediately like above, immediately like below? Like if we're looking down on the ground, or immediately behind, immediately in front. Like these would still be sub properties of next to. No?
I think what it would be is you have next to, and then
Like-
you would have the subproperty under next to would be to the right and to the left. and then immediately to the right and to the left, because the thing is you could say, oh, he lives next to me, 2 houses down to the right. He's still next to you. Like, and next is just, it's very vague.
To
Correct.
the left,
If I'm complicating things too much, I apologize.
to the right.
You usually do, Jay.
Yeah, well,
What did I walk into? What a great conversation. I've been sitting over here listening to you. Been going great. Fantastic. I'm gonna make you now.
well, the hard part, I mean, the guts, John.
We were almost done, John. See, now you
Oh,
stole
I
our
know.
thunder.
Oh, I
Yeah.
know.
We were
I
so
mean, I
close.
guess
We had it.
Are you?
It was easy.
Oh,
We
so
were
that
like,
was
come on.
off.
Oh, I don't think you're almost
He's
there.
trying. He's
What
trying.
we're
Yeah.
trying to do is just keep it as simple for as long as we can.
That's exactly right. That's the advice I was giving the rest of the crew over here too. They were talking about, for example, should we introduce inverses? And I was like, do you need to introduce inverses?
We have some inverses that
We
we
only have the inverses that we need.
Yes,
Yep.
we go. There was also a question about whether there should be a general right of and then a sub-relation of immediately to the right of. And I was like,
that's what we have. We're talking about
both,
right now.
or do you just need one of those? Is it a subclass or a sub-relation of next to? If you only have one of them, that would be a way to simplify the logic. And when I was doing this, it was basically simplify, simplify, simplify. I'll also give you another pro tip, 2 more pro tips. One, I like wrote out the problem on paper. And so I wrote out the inferences I would need to get to the answer. And then I modeled all of that just like I'm modeling these 1 through 15. In fact, I didn't even need all 15 of these. I just modeled the proof, basically. That's how I solved it. That's one thing. The other pro tip here, can you guys see my screen?
No, sorry, I'll stop sharing my
No,
screen.
that's fine. Just want to make sure. The other pro tip here is there. Enumerating. You can define a class as the enumeration of instances, if you recall. There's a hint. So I have a class of houses that is just no more, no less, red, green, ivory, yellow, and blue.
All right, so we did that sort of, but we haven't done the enumeration part. I don't even know how to do that.
You can just type it into Protege. You say define class, and then you could either just type.
Here, Matilda, can you share so you can show?
You just say red or
1 second.
or you can put the set notation around.
Is that the equivalent to?
Mhm.
I'm making an adjustment. 1 second.
Okay.
Here, you want me to stop sharing so you can do? Go right ahead.
Yeah, go ahead and share.
To the right
Oh.
of ivory. Okay, share screen.
Curious to know where to do this.
Share this.
All right.
Editor says it's waiting for class name, object property name, data.
All right, so John, how do we,
With the set symbol.
here, Matilda, go to the class and he can see where you have all the instance for the houses. So we have the houses there, John.
Yeah.
Here, go to house.
Mm-hmm.
So you're saying that we can enumerate that, or?
Yeah,
we
go
can-
to equivalent to,
Oh.
and then go to the class expression editor.
Second tab. Yeah.
Now just type in either just blue or set bracket blue. It may be bracket blue.
Is that a set bracket?
Yeah, and then close bracket. I can't really see it. Is it?
Oh, sorry. I don't know how to make this bigger.
Yeah, that's fine. And then space. And then put or. And then do it again with green, ivory, red, and yellow.
And so what is that doing from a logic perspective in Protege?
From a
For the-
logic perspective, it's saying that anything that is a house is one of those.
Only 4 of them there. You need a 5th.
Or
house.
And
yellow,
then
right?
any of those 4 or 5 are instances of house. And so the whole set, like the whole class of house is exhausted specifically by these 5 things.
Okay.
Nothing else is a house.
Okay, should we do that with cigarettes and everything else?
I did.
Is an animal owner.
And it's because there's like closure in here. So closure in the sense that you're only really concerned with these these instances, right? These animals, these cigarettes, these houses, right? And so you can kind of cordon off the rest of possibility.
So is this sort of like bringing in a way, what they were talking about earlier with like set theory and
Yeah.
kind of like
Yeah.
what you would want to do in an open world assumption if you had, say, I was building an ontology for a drone and I
Mhm.
want the drone just to care about these type of things, then the drone would only focus on these things because I don't care about like small children at the
Right.
border. I care about like big looking bad guys with guns or something.
That's right. And if you were to just put the instances there as you have, then you're not excluding other things as being instances.
So it could start to look for
That's right.
other things.
You could run a reasoner, like here's two cases. You have just the instances listed. You could have some object properties that entail something else as an instance. If you have it if a class enumerated and you have object properties that entail some other thing that's not included in the enumeration as an instance, you'll get a contradiction.
You're doing location wise.
Kind of, not literally, but.
Yeah. Like this household is like a box and there is a
How about
Right
you
now-
put there in old gold's
net
Drinks.
and a drink.
So, enumerating it like this
Have
entails
old
that
gold
there's
to be
nothing
old
else
gold.
in that class.
I was gonna change it, Jay, to
Okay.
old golds, just to be consistent.
Yeah, it's entirely exhausted by those enumerated elements. Yeah, Robert.
Does the way you categorize the relations, for example, like you had mentioned to the right of is a sub property of next to, does that really impact the outcome?
Immediately to the right of.
Yeah.
That's fine.
Like,
Only if you don't need
Let's stick
more
with that.
general right of. And yet-
Classes, for sure.
but like in general, because that's sort of like, I don't know, it's pretty conceptual, like how would you know to do that?
Here's exactly how I knew. I said, I don't need a general right of. So I'm only needing to use immediately to the right of. I need to use next to. I know immediately to the right of any two things that fall in there, like any pair, are going to be next to each other in every case. So that's a subrelation. And then I said, well, I don't need the other relations that would be nearby. The reasoner is not going to use them.
Oh, so it's for simplicity's sake,
That's
but
right.
you could still do to the right of.
Absolutely. You can do as much
Okay.
as you want.
It's-
This is more like problem solving strategy.
Yeah.
But it
like
just might not be as
minimal.
definitive.
You're streamlining it, okay.
Makes it easier for me to comprehend. I don't think it makes like a big computational difference in these cases, but
Yeah.
like, it's easier for me to think through. I'm always simplifying.
Gotcha, thank you.
And then I can complicate however I want. With that, I'm gonna make you stop. Time. I'm gonna move on a little. Don't worry, we will come back to that next time. In fact, I will give you a similar puzzle. It will be simpler, significantly simpler. It will give you insights into how to solve this one. We will hit this one not the subsequent week, but later downstream. So we'll be back. Don't worry. Yeah.
Could this be a paper?
Maybe. You can solve it. It is a very good exercise for learning the intricacies of this stuff, I find. But I do want to talk about the projects too. So here we go. All right. I had some strategies that I used that I thought I'd share with you when I was exploring, the role constraints that you were tasked with discussing in project one. So for instance, suppose you're checking combinations of role constraints on object properties in L2 with the direct semantics, like you're exploring what pairs can be expected in a set defining an object property that's both symmetric and transitive. I don't know, off the top of my head. Transitivity defined there, symmetry defined there, all in terms of X, Y, Y, Z pairs under a relation R. Right. So you might proceed as follows. Suppose there's some pair AB and BC under the relation. By transitivity, AC is in the relation. By symmetry, BA and CB and CA are in the relation. By transitivity, again, AA, BB, and CC are in the relation. And just so you're not lost on that, here's why, right? Like you can connect it through. You get the reflexivity basically because of transitivity and symmetry. So this ultimately, if you walked through this step by step, you'd get R as defined as this set of pairs. You might ask yourself, have I explored all the combinations? You might not know when to stop, basically. Here's a heuristic. For n individuals, there are n factorial non-reflexive combinations. And if you grant reflexive pairs, there are n factorial plus n combinations. This is just like straight combinatorial counting. I'll give you an example. So an n factorial, by that, I just mean that n, like exclamation point, and that is equivalent to essentially just like taking n, multiplying it times n minus 1 times n minus 1 times blah, 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 all the way down to 1. That's it. So suppose you assert A, B, and C are in the domain. That's n of 3. You get 1 pair, 2 pairs, 3, 4, 5, 6. If you allow for reflexivity, 3 more. So 9. N factorial, you have 3 for n. N factorial itself is 6. If you allow for reflexive pairs, n factorial plus n, 6 plus 3, 9. So how do you know you're done? Did you have 9 pairs? Now, that won't tell you in every case that you finished, like maybe you don't need all 9, but it does tell you which ones to check and when you know you're done checking. So when you're exploring possible individual pairs under a given object property, save yourself time and first identify the number of possible pairs to explore. 3 individuals, 9. So you know when to stop looking for them. And also as a way to identify pairs to test. Only 9 options. Check them out. So we have here 9 pairs. Transitivity and symmetry, 9 pairs. You don't need to explore anymore. Observe, this entails reflexivity. Because in the domain you have A, B, and C. R is reflexive. And this is from snapshots from Protege. Well, I'm just showing you the inferences that were drawn out by the reasoner. Look at there. There's what I asserted. Little a is A related to B. Little b is A related to C. Inferred. Little a is related to A related to A. Little c is A related to C. This is reflexivity.
That's not the project we're working. We're working with.
Just giving you heuristics. Yeah, walking through.
Okay.
That's right. I'm getting there.
Okay.
I just want you to because this can be transposed in the key of the project, right? Like this is a heuristic that's useful across all of these exercises.
Yeah.
So here, symmetry is another. Suppose B is a subproperty of A. This is closer to what you guys are doing, right? Subproperty stuff. If B is symmetric and AB is in big B and BC is in big B, then this follows. You get AB, you get BC, you get BA, CB, and A. You're basically mirroring. Remember, because I'm talking about what's in B. And B subproperty means anything in B is populating up to A. This is telling you that if B is symmetric, then so is A. Because what's in B is in A. Not so interesting, right? Suppose B is a subproperty of A. B being irreflexive with AA and A is consistent. If B is irreflexive and A has a reflexive pair, that is consistent. You don't get a contradiction. But if A is irreflexive and AA is in B, you get a contradiction. Irreflexivity does not populate up, but it populates down. If A is irreflexive, so is B. If B is irreflexive, it doesn't mean A is. Does that make sense? And this is how I tested it. This is another heuristic. If B is irreflexive, I made B irreflexive, and then I dropped A as an individual is related to itself. under A as a property, right? I just created instances and I A related them to each other, to themselves. And then I noted, I ran a reasoner, it was consistent. I did the same thing, but with B, and I flipped and made A irreflexive, and that it was a contradiction, generated inconsistency. I didn't need to do that because I could have just thought about the underlying logic. So the underlying logic is as follows. If B is irreflexive, that means nothing in B is B related to itself. That's what it means. It's irreflexive. There's no reflexivity for any of the pairs. If that is the case, then none of the pairs in B are they can be irreflexive, but that says nothing about what is in A, because the condition for subproperty, for B being a subproperty of A, is that if something's in B, then it's in A, not if something's not in B. Does that make sense? Other direction for A being irreflexive means that there is no, in the scope of the A's, there's no things that are related themselves. Nada. Anything in B is in A. If AA is in B, that means AA is in A. But that can't happen because nothing of that sort, of that structure, is in A. Contradiction. So you'll note, you'll start to note in a second, there's a pattern for populating up and down. I showed you one a minute ago. Like some of these relations you can like figure out. You can just look at them actually at this point. You will be by the end of, but in a couple of slides, you'll be able to see which ones populate up and which ones populate down, because some of these have negations in them and some of them don't. Irreflexivity, the semantics for it involve saying what's not the case. Knots don't populate up, but they populate down. Absence of knots populate up, but not down. Suppose B is a subproperty of A. B being asymmetric and A being symmetric is consistent. B being symmetric and A being asymmetric is inconsistent for the same reasons I just described. Asymmetry doesn't populate upwards. Some summaries. Symmetry goes up, not down. Transitivity and reflexivity go up. Well, transitivity and reflexivity go up. Transitivity doesn't go down. Reflexivity does. Because reflexivity is evil.
If B is a subproperty and B is reflexive, then it's consistent with A being reflexive and vice versa.
You just said two things being reflexive. Did you mean to say irreflexive?
No, but A and B,
Mm-hmm.
so if B is reflexive, then it
Mhm.
would mean that A has to be reflexive.
Yeah.
If
Reflexivity is the oddball, because reflexivity works everywhere. It's global. Test it.
John,
Yeah.
I have a question.
Mm-hmm.
Is this universally true? So if you say something like asymmetry can't populate up, so
Mhm.
would that mean that that B if B would be in conflict with inverse of A?
Oh, I don't know.
So does it work only up in its own chain, or does it work up in the inverse of its own chain, or down?
I believe in just about every one of these cases. Anyone that I've checked, I believe they mirror each other.
So if that's the case, and you said, okay, well, irreflexivity can't populate up, then that would mean that if you had B, then it's not going to be irreflexive with inverse of A.
Let's see. Let's test it. Lay out the case. Let's try it.
They get my protege going. Hold on a
Yeah,
second.
love it. I'm gonna
Uh,
let you share. Well, you guys got a chat going. Yeah,
We're trying.
I love it.
Yeah, I kind of want to work on this outside of class now.
Oh, I know you do. Why I made you stop.
All right. I'm gonna share my screen or something.
Right, yeah, go for it.
All right, hold on.
Let's walk through it.
So we're doing irreflexivity. Okay, hold on. Thought I still had my little thing I modeled the other day, but I don't. All right. Okay. See my protege?
Yeah.
All right. So we're gonna have we're gonna have B. We're gonna have, sorry, AI. And we're gonna have BI. What am I doing? We're gonna have BI. Okay, and now I have to make and then I have to make B inverse of. Okay, so what I said was, can something be irreflexive, right? At B,
Mhm.
and then it goes up to AI, right? So that would make AI irreflexive also.
Let's see.
And now I'm gonna run my reasoner. It worked. So I guess that law doesn't apply across the inverse.
Let's put an instance in and see what happens. Oh, you got all this stuff.
Well, I was doing this before.
Yeah, it should be all right. Let's just
Yeah.
put an instance.
I'll just put myself as an instance
There we go.
of
Oh, you don't have to make it a type of anything.
well, I will.
All right.
What is going on here? What is going on here?
Says it's a slip.
Where's my brain isn't working very well.
Sorry.
All right. There we go. Now should I run it?
Let's see. Go back to individual. Let me make sure you got a. All right. Yeah. Try it now. Let's see what happens.
I think it's gonna work because the reason. Yeah.
You got. Well, let's look at it. You've got J is A related to J. So reflex. You got J is A inverse related to J. So then both the A and the AI are reflexive.
So that means that the chart you have, it only applies to, it doesn't apply to the inverse.
So you click irreflexivity for B, right?
Irreflexivity for B.
Chart I have says that
And
irreflexivity
oh, hold on.
does not populate up.
Hold on. I did it wrong. It's
Got
gonna
right.
fail. It's gonna watch. Or maybe it won't. I don't know.
Let's see. I love sanity check.
Why won't it let me start the reasoner?
Let's see what you got. I'm not sure.
Hold on. So we said we're gonna have irreflexive for B and irreflexive for A.
I think you wanted to make B reflexive.
What's that?
I think you wanted to make B, so irreflexivity doesn't populate up, but it does populate down. And so you should get an inconsistency if B is reflexive.
It won't even let me run the reasoner right now with that.
That's interesting.
That is interesting. All right.
Stop the reasoning?
All right, so inverse of A is irreflexive,
Yeah,
and B you want reflexive?
yeah.
My reasoner decided to stop working.
Do you
Got a
have
lot.
any reasoner selected?
Yeah.
Oh,
select-
oh, yeah, that's weird. That's weird. All right, hold on.
That's why it's all working.
Yeah,
Let's check it. There you go. Inconsistent.
inconsistent.
Yeah, and this is just to the same piece, right? So irreflexivity doesn't populate up, but it does populate down. And so if you
But
say,
it didn't give me, John, it didn't give me the little thing in the corner.
click on the A or the B right there, the little red.
Usually does not like that I'm doing a live stream with
It
it.
really doesn't. It's like,
really-
don't show off what's going on.
I think my protege just died. All right, I'm gonna stop sharing.
Okay.
What a piece of crap.
Do you want me to try?
Yeah, give it a shot. Let's do it. Let's play around.
Okay, one sec.
What
Let
do I
me
wanna do?
let me pull open.
Oh, let me move my shoe out of the way.
Can't believe protege died. I'm right in the middle. It's big chance.
Protege can.
It likes to die all the time, right, Tim?
It does.
All the time.
You know,
Okay,
I'm
so-
conversations with some groups to create a replacement. Yeah, so let's see.
Okay, so
All right, you got him.
I don't think it likes me doing either. Okay, there we go. So what do you want me to click?
Let's see.
A,
Let's play around. We're checking out. We're testing this.
because mine was having a lot of issues earlier, and Jay and I
Okay.
briefly spoke over chat, and we didn't get to figure out, like, I didn't get to figure out what was wrong with it.
Okay.
So
Gotcha.
we want to try A is irreflexive.
Yeah. A is irreflexive. Did it just crash? No.
No, sorry, I pulled up my VS Code because I have the tables.
Yeah, I see.
Okay. A is irreflexive,
Mhm.
and
And then B inverse.
B inverse.
Yeah, is reflexive.
B inverse is
No,
reflexive.
no. So B
B inverse is
so
reflexive.
BI, and that's
Okay.
that's
Reasoner.
Yeah.
With hermits, okay, start reasoner.
Yeah, there you go. You click over there, it'll tell you. It'll give you some hints. I can't see them. So if you clicked on the, I was saying click on the far right icon. Yeah, right there.
Yeah, it's not showing up.
Oh, okay.
It normally shows up.
Interesting. It really doesn't like.
It's
to
not
share
showing up right
information.
now.
What if you click on the red A? Nothing.
Wow, I think Protege doesn't like anybody's computer with
Okay,
Zoom.
go to Reasoner. Up at the top, and it should give. Well, not even let you. Oh my God, that's crazy.
Hold on, let me see if I can close out of some other stuff. And see
Wow.
if that helps.
That's crazy. Not happy.
Yeah,
with
no. No
Yeah.
luck.
it. Well then, we found a different bug than the one we were hunting. That's fascinating. Huh, okay. You see
I
the
guess we'll have to
strategy?
try off screen and do it again.
Yeah. You see the strategy?
Yeah,
Okay.
but there's still one thing I have no idea.
Go on, tell me more, Giacomo.
Proving how.
Ah,
How to prove unsatisfiability, average contradiction.
yeah,
I have
that's
no
straightforward.
idea How to prove that a rule chain is complex.
Well, you didn't figure that part out.
So stuff like transitivity and I don't know, mostly transitivity stuff.
Yeah. So Giacomo's asking, how do we, sorry, I'm just sharing my screen again. He's saying, okay, I understand how to prove inconsistency. If I like make a rule chain and it pops up and it's like, you got inconsistency, or you can just prove it by hand. You can demonstrate that something's inconsistent. There's some pair or some chain that's inconsistent. You know how to do that. That's easy peasy. What happens when you get in those scenarios where you have, non-simple chains is what the debugger will say. So how do you demonstrate like that's what's going on, or like that's the explanation? So the way we will do it for the purposes of this paper is we'll just say there's a non-simple chain, and then we'll cite the papers. But the more technical answer to your question is it's quite complicated, but the long and short is that there are known proofs that establish that those property chains that are generating the non-simple issues can simulate the halting problem. So there are papers on papers published about the decidability fragments. And so we will cite those papers, and I know which ones they are. I know where to point. And so to justify all this, like the debugging that goes on that you see in your protege. But roughly speaking, that is it. And that is how you deal with like well, let me back up. The reason I'm not going through that here is it involves a different kind of proof method than what we'll be talking about, and it will kind of be a detour, but it involves like reducing chains of like algorithms or languages to other known problematic algorithms, and it gets into the domain of like NP completeness, P completeness, EXP completeness, and stuff like that. And so, but that's where we will cite and point. I just didn't want, that would take us like quite a bit of time just to explain. So it's a reductive proof that demonstrates that stuff. And it's existence proof that demonstrates that stuff, and we can just leverage that work.
So when we're doing exercise 2, number 2,
Yeah,
and we have like unsatisfiability for like,
yeah,
A is symmetric and AI is asymmetric or whatever,
Yeah.
we can create a proof for unsatisfiability.
Mhm.
When we get that, I don't know, A is transitive and AI is inverse functional,
Yeah, yeah.
whatever, and it tells us this is a complex chain,
Mhm.
we just tell you this is a complex chain.
Yeah. But it is quite complicated, right? It becomes very complicated.
Yeah, like many people, like I've actually read a couple of, even the handbook we were looking at last year.
Yeah, yeah.
They never talk about this in detail.
Yeah,
They
no,
always
they don't.
gesture
The
at it.
one place they bring it up, they talk about regular property chains, and what they say is they go, these property chains have to be regular. The details are very technical, so we won't discuss them here. It's a textbook about this topic, and they're like, nope. But they do cite all the papers for the most part, because Ian Horvitz is one of the authors of that book. They cite the papers that would point you to the details. This, by the way, this is a description logic textbook. There's one out there that like Ian Horvitz and some other folks put together like a few years ago. It has many of the details of the stuff that we've discussed here. Nothing like this, none of the practical applications, but like a theoretical background. And what we're laughing about is there's a point at which they start to get to the place where they would explain what I asked you to explain in assignment 2, and they're like, nope, it's too technical. So yeah, upshot, I'm not gonna make you do that. I didn't want you to struggle with it and think about it. And now you know how, now you have a glimmer of how complicated it is. Roughly speaking, all you need to know though is that there are theorems and demonstrations of like that or that justify the sort of like non-simple blocking that goes on in DL. And if you want to know anything more about that, essentially just keep in mind that there needs to be, for property change, you just need to have a strict partial order, basically like transitivity over the like chains that link to, or roles that link to other roles. And you will be trying to avoid, whenever you're doing this, if you want to block off undecidability, you'll be looking to avoid loops or branches that collapse in that property chain. That's it. That's basically it. Like you want to have a chain that's linear. So A to B to B to C to C, because those things are easy to like run reasoning over. They create tree branches like a tableau that you can just run down. If you have to start creating tree analytic tableau branches that refer back to other branches, which is what happens if you introduce things like a property that's functional and transitive, then you're going to violate those issues. You're going to be able to like produce something that's undecidable. So again, like that's a high level. I would, the technical details will take us way too far afield, but that's kind of what you need to know, right? You need to know, well, one, already you know more than most people at this point because you were struggling with it. so you know which combinations you can do and which you can't. Already practical wisdom right there. For the purpose of the paper, we don't need to go into the details. So
Are there
yeah.
some of these relationship agreements, or conflicts or that like you're almost never ever going to use, if we built them, we would almost never use them in a real world application ever?
No, I think that I'm sympathetic to what you're saying. I think the reason it's easy to think that way is because people have been too afraid to try.
Yeah.
I
I feel
actually
like
have
there's so many times you try to find an example and they
Yeah.
use the same example. Like it'll be like the girl and she's this tall, but she can't be taller than herself. And it's like over and over again when you look up different things in reflexivity and transitivity and everything, they're using the same examples over and over again.
Mm.
And it's like, I want more real world examples
Yeah,
because the more real world examples I get personally, I don't know how everyone else feels. That's when I start to really understand it.
that's where the logic comes in.
Yeah.
Come on, Star Dog. Stop giving me the same stupid examples. Show me how the reasoning works. No, that's exactly right. I actually later in the not much later than this, I have a lecture that I'll give on like other heuristics for thinking about broader relations and properties of relations that's going to overlap significantly with this, but it will also talk about role constraints that are not discussed in OWL. You know, we'll give you heuristics uh, that will help you like determine when object properties are the same and when they're not, but also a recipe associated with it for how to come up with interesting, like logically sophisticated object properties. So yeah, that's definitely on target for the class.
You think that the more complicated relationships are at the instance level and not at the universal class level?
I think there are more, like certainly more complicated. You're going to see more complicated object property and role constraints at the instance level because the world is messy. But
Yeah.
I do think that there's a large space of class level, like role constraints that haven't been explored because
No, yeah.
people have been afraid to like break things or
Yeah.
they're not comfortable like without they're afraid to go too much because they make too much because they think it's fragile and they also don't understand how the logic works. Again, you guys
They don't
are
want to deprecate.
ahead of the curve. So I asked you to do something very, very challenging and you did, but I also asked you to do something very, very practical en route to doing something very, very challenging. And now you've learned something very practical and also how challenging something is, which is progress. So with that, I have to call it. It's 3:40. So I'll hang around if anybody has questions, but